Alright guys, welcome back. We're going to be solving another question from the second chapter of the Mechanics of Materials by Johnston. And in this one, for the steel truss that we can see, we have the elastic modulus of 200 gigapascal and the loading that we can see on top. We need to determine the deformations of members AB and AD, knowing that their cross-sectional areas are 2400 millimeters squared and 1800 millimeters squared respectively. So what we are interested in here is the force in AB and AD, and the formula that we have in here is the one that we discussed over and over in the previous video. So we have deformation is equal to force, or P, times the length over area times elastic modulus. And going for each of these two members, we obviously need the length of each member, the force in that member. We have the same elastic modulus, so E is also the same, but we have different areas for each of them. So before doing that, we need to figure out the forces in AB and AD, and since we are in equilibrium, we can use our equilibrium equations, and it makes sense to draw the free body diagram for point A. We're gonna have the free body diagram of a particle. So before moving to that, so we have a pin at point 8, which means we normally consider two components, AX and AY for here. And since at point C we have a roller, we're gonna have only a normal force, or a force in Y direction. Let's call our X and Y in here. But like looking at the free body diagram of whole truss, we'll see that we only have one force in X direction, which means our AX is actually 0. So when we are trying to draw the free body diagram for particle A, we don't consider any AX, which is coming from the, again, free body diagram of the whole truss. So we're gonna have the AY in here, and we're gonna have the force FAD and FAB. I'm just gonna consider one random direction for now, but we're gonna figure it out. So now we have three unknowns, so we need to figure out the AY. And because of the symmetry of this truss, if we do the sum of all forces in Y direction, again for the whole truss, we have 228 kilonewton applying in the middle, which means AY is equal to CY is equal to half of that amount. So 228 divided by 2, which is going to be 114 kilonewton. So that's how we find the AY. By the way, I have a separate channel for engineering mechanics and statics question. I'm going to put the link in the description below. If you need more practice in that sense, I have a separate channel for this topic. So let's do sum of all forces in X and Y equals 0. So for doing that, we need to have some sort of information about this angle. Maybe you can call it alpha, which is the angle here. So if we look at this right triangle, we have the base 4 meter, the other side would be 2.5. So if we just do a Pythagorean theorem, we can find the hypotenuse, which would be 4 squared plus 2.5 squared. Let's see what we get for that. So the square root of 4 squared plus 2.5 squared is going to give us the hypotenuse 4.717. So now we should be good to go to find the x component. So obviously we have the F80, which is in the positive direction of x, and again this is our positive direction for x. So F80 plus the x component of FAB, which is going to be cosine of alpha, or 4 over adjacent over the hypotenuse, 4.717, and this will be equal to 0 because of the equilibrium condition that we have in here. So sum of all forces in x is equal to 0, and same for the y. So we have two unknowns. We cannot do anything in here. So let's move on to sum of all forces in y direction. We're going to have AY, which is 114, and the top part, so positive, plus the y component of FAB. That's going to be upward too. So this time we'll have the sine of alpha. So FAB sine of alpha would be 2.5 over 4.717 equals 0. And we're going to get FAB negative. So 114 times 4.717 divided by 2.5. Let's calculate this. So 114 times 4. Divided by 2.5. So this is going to be negative. Again, we have a negative sign. which shows that the FAB is actually in the opposite direction. So 215.1 kilonewtons, and the negative sign shows that the FAB is actually in the opposite direction. And since the member is somewhere in here, based on the Newton's law, the force would be in this direction. So this member would be in compression, which we're going to show it with C. And that shows we're going to have a member that is compressed. So our deformation has to be negative because it's going to shrinking. All right, so now that we have the FAB, we can find FAD pretty easy. So from our FX in here, FAD would be basically negative FAB, so negative 215.1 times 4 over, so this times 4 divided by 4.717, and this is going to give us 182.4 kilonewton, and no negative sign. That shows that that's the correct direction for FAD. So here the member would be in tension. So we're going to expect the positive deformation for this because it's kind of getting elongated. So we'll have positive. So the rest of this is pretty easy. You just have to put these forces in our formula in here and we can figure out each of the answers. So let's start with the deformation of AB, which again is going to be the force in AB, length of AB, the elastic modulus is the same, and the area that we have for AB, if you look at that, we'll see it's 2400 millimeters squared. So for the force, we're going to have negative 215.1. I'm just going to multiply this by 1,000 to get it in Newton. The length of AB is basically the hypotenuse of this red triangle that I showed in here. So 4.717, and the unit is in meters, so that's good. The elastic modulus we had in the question, 200 gigapascal, so 200 times 10 to the 9 Pascal. And the area, as I mentioned, is 2400 millimeters squared. So we're going to do 10 to the minus 6 in order to get it in meters squared. And that's going to give us the deformation in meter. Let's see what we get. So minus 215.1 times 1000 times 4.717 divided by 200 times 10 to the 9 times, or actually I'm going to do 10 to the 3 because we can cancel these two, and times 2400. So this is going to be minus 2.113 times 10 to the minus 3 meter, or minus 2.113 millimeter. And we're going to have similar story for the member 80. Again, same formula, so we just have to put the force that we have, 182.4 times 10 to the 3 to get it in Newton. Since we had it in kilonewton, the length of 80 would be this side of the triangle, 4 meter divided by same elastic modulus for the steel 200 10 to the 9, and the area that we have for 80 would be 1800 millimeters squared. So, and this should give us the final answer for this. So 182.4 times 1000 times 4 divided by 200 times 1800 times, again, 1000. We're going to cancel out these two. This is going to give us 2.027 times 10 to the minus 3 meter, or 2.03, or let's just be consistent, 27 millimeter. And that's going to be the final answer for this question. Hope everything was clear. Let me know if you guys have any questions. You guys take care. I'll see you in the next video. Have a good one.